Good evening, my dear listener. Or perhaps it's deep into the night where you are. Welcome once more to your midnight library, a quiet place where knowledge meets rest. Tonight, we're leaving the familiar glow of our solar system behind, drifting slowly, ever so slowly, into the vast and silent depths of the universe. We're setting out on a serene journey toward a black hole, one of the most mysterious and beautiful wonders of cosmos. Along the way, we'll linger on the profound discoveries of Stephen Hawking and explore the many gentle cosmic treasures connected to these hidden giants. Everything we share tonight comes from real astronomy, real physics, softly woven together just to help your mind unwind and your body surrender to sleep. Close your eyes now, if they aren't already. Take a long, slow breath in. Feel the air fill you gently. Hold it for a moment and release it, softly, completely. Again, inhale peace. Exhale any lingering tension. Feel your shoulders soften. Your arms grow heavy. Your legs sink deeper into the warmth beneath you. Your mind is free now, light and floating, ready to travel through the stars with me. Imagine we're together in a quiet spacecraft, no engines roaring, just silent gliding through the void. The Earth is a distant blue marble behind us. The moon has silver memory. Ahead, the Milky Way spreads like a river of soft light, billions of stars whispering their ancient stories. We're heading toward a particular place, a stellar mass black hole, born from the quiet end of a massive star. But before we arrive, let's take our time. There's no rush in the cosmos. Let's begin gently with the life of the stars that create black holes. Every star you see twinkling on a clear night began as a vast cloud of gas and dust, mostly hydrogen, drifting in the cold of space. Over millions of years, gravity pulls these clouds together, slowly at first, then with growing strength. The center heats up, pressure builds, until nuclear fusion ignites, and a star is born, shining steadily for billions of years. Our sun is a quiet, middle-sized star, content to burn gently for about 10 billion years total. But the stars that become black holes are different, far more massive, 8, 20, even 50 times the mass of our sun. They live fast and bright, fusing hydrogen into helium in their cores, then helium into carbon, oxygen, all the way up to iron. This process releases the energy that makes them shine so fiercely. But when iron forms in the core, fusion can no longer produce energy. The balance tips. In a single dramatic moment, the core collapses, sending a shockwave outward in a supernova, one of the brightest events in the universe. The outer layers explode into space, enriching the cosmos with heavy elements, the very stuff that will one day form planets, and even us. What remains of the core depends on its mass. If it's light enough, it becomes a neutron star, an incredibly dense sphere where protons and electrons merge into neutrons. A teaspoon of its material would weigh as much as a mountain, spinning rapidly, sometimes pulsing as a pulsar, sending gentle beams of radio light sweeping across space like a cosmic lighthouse. But if the core is heavier, gravity overcomes even neutron pressure, and collapse continues all the way to a black hole, a place where matter is compressed beyond imagination, surrounded by that soft boundary, the event horizon, the point where space-time curves so deeply that light itself follows a path with no return. There are three main families of black holes we know today: stellar mass ones, like the one we're approaching, formed from single massive stars or mergers in dense clusters, intermediate mass ones, rarer, perhaps born in crowded star birthplaces where many collisions happen over time, and the supermassive giants, millions or billions of times our sun's mass, sitting calmly at the centers of nearly every large galaxy, including our own. The supermassive black hole in the Milky Way is called Sagittarius, a star. Astronomers watch stars orbiting it for decades, tracing invisible paths, proving something massive and compact lurked there. In 2022, the Event Horizon Telescope, a worldwide network of radio dishes, captured the first true image of it, a soft orange ring of glowing gas surrounding a dark shadow, the silhouette of the event horizon itself. Later, in the galaxy M87, an even clearer portrait emerged, showing the same peaceful glow, proof that Einstein's ideas hold true on the largest scales. As we continue our quiet journey, feel the spacecraft gliding smoothly. The stars grow fewer ahead, space darker, yet peaceful. We're still safe, many millions of kilometers away, but already subtle changes appear. Distant starlight bends gently around the black hole we're approaching, creating multiple images, faint arcs and rings, a phenomenon called gravitational lensing. Einstein predicted it over 100 years ago, and today we use it as a natural telescope, magnifying faraway galaxies hidden behind massive clusters. Now, closer still, a beautiful structure comes into view, the accretion disk, hot gas and dust, torn from a companion star in a binary system, orbiting the black hole in a vast, flat spiral. Friction heats the inner parts to millions of degrees, making it glow in X-rays and visible light, soft blues near the edge, deepening to warm oranges and reds closer in. The disk spins gracefully, matter falling inward in slow, elegant streams. Some black holes in binary systems, like the famous Cygnus X1, discovered in the 1960s, show this dance clearly through their X-ray flickering, observed by satellites drifting quietly above Earth. Sometimes, powerful magnetic fields twist above and below the disk, launching narrow jets, beams of plasma traveling almost at light speed. These jets can pierce through galactic gas clouds, stretching for tens or hundreds of thousands of light years. They carry away energy and angular momentum, helping the black hole feed steadily. In distant quasars, these processes shine so brightly that a single black hole can outglow trillions of ordinary stars, lighting up the early universe. Quasars were mysterious at first, discovered as bright radio sources in the 1960s, looking like stars but with strange spectra. We now know they are young, active, supermassive black holes, devouring surrounding gas in the crowded centers of forming galaxies. Their light has traveled billions of years to reach us, showing us the universe when it was only a fraction of its current age. Let's pause here, drifting peacefully, and turn our thoughts to Stephen Hawking, a gentle, brilliant soul who spent decades contemplating these cosmic secrets. Despite the challenges of his illness, he communicated profound ideas that changed how we see the universe. His most famous contribution came in 1974, when he showed that black holes are not completely black. Quantum physics tells us that empty space is never truly empty. Tiny particle-antiparticle pairs constantly appear and disappear, borrowing energy for the briefest moments. Near a black hole's event horizon, the intense gravity can separate these pairs. One falls in, the other escapes, carrying away a tiny bit of energy. From far away, this looks like a faint thermal glow, now known as Hawking radiation. This glow is incredibly weak for large black holes, cooler than the cosmic microwave background, that gentle afterglow of the Big Bang filling all space. But it means black holes slowly evaporate, losing mass over unimaginable timescales. Only microscopic black holes, perhaps formed in the universe's first moments, would evaporate quickly, releasing energy in a soft final burst. Hawking's work also revealed that black holes possess entropy, a hidden measure of complexity proportional to the area of their horizon. This led to the beautiful black hole thermodynamics laws, mirroring the familiar rules of heat and energy, and it sparked deep questions about information. What happens to the details of everything that falls in? Hawking first suggested information might be lost, but later ideas, including his own evolving thoughts, propose it's preserved in subtle ways, perhaps encoded on the horizon or returned in the radiation. These ideas continue to inspire physicists searching for a unified theory of quantum gravity. Another gentle wonder connected to black holes is gravitational waves. When two black holes orbit each other in a slow binary dance, they spiral closer, radiating ripples in space-time. These waves carry energy away, speeding the spiral until the final quiet merger. In 2015, the LIGO observatories detected the first such signal from two stellar black holes 30 times our Sun's mass each, merging 1.3 billion light-years away. The chirp lasted fractions of a second, but told a complete story. Since then, dozens more detections, revealing an unexpected population of heavier black holes, perhaps formed from earlier mergers in dense star clusters. On larger scales, supermassive pairs in merging galaxies produce lower frequency waves, detected through careful timing of pulsars across the Milky Way, creating a soft gravitational wave background, like a cosmic ocean swell. Black holes play a quiet but crucial role in galaxy evolution. Their accretion and jets provide feedback, heating gas to prevent too rapid star formation, helping galaxies grow steadily over billions of years. In the very early universe, the first quasars helped ionize neutral hydrogen, clearing the fog and allowing light to travel freely, marking the end of the cosmic dark ages. Now, as our journey nears its gentle close, imagine us turning slowly away from the black hole. The glowing disk recedes, colors softening into the distance. The lensed stars spread back to their familiar patterns. The vast quiet returns, comforting, infinite. Black holes, once thought only as endings, are revealed as part of the universe's great patient cycle. Matter transforms, energy flows, information endures. The cosmos is stranger, deeper, and far more beautiful than we once dreamed. Let these thoughts settle softly within you, like stardust drifting in moonlight. Stephen Hawking showed us that curiosity and wonder can shine even in the darkest places. Tonight, you've traveled safely through the stars with me, feeling the calm of deep space. Your breathing is slow now, steady, peaceful. Your body completely relaxed, heavy, warm. Your mind adrift among gentle constellations. The midnight library lights are fading, very softly. It's time to let go completely and surrender to deep, restorative sleep. Sweet dreams, my dear friend. Rest well until we meet again under the stars.